This presentation will discuss the topic of utilizing the LLVM toolchain and the LLVM intermediate representation as a target for compiling functional languages. But why focus on compiling functional languages specifically? Well, functional languages revolve around the idea of composing and applying functions together without introducing the concepts of mutable state and side effects. It's similar to the mathematical definition of a function. Given some specific inputs, you will always receive the same output. And in languages, this is known as referential transparency. It's the notion of being able to replace some subexpression, like a function call, with another subexpression, like the value returned from that function, without changing the semantic value of the expression as a whole. This turns out to be pretty useful when writing a program, as your units of code, your functions, now have deterministic predictable behavior, which is easy to understand. And because functions are now deterministic, implementing things like parallelism is easier, as there's no shared state to keep track of between executions. The problem is when it needs to be compiled, because computer systems and machine code are inherently procedural, with mutating memory being the primary method of computation. The work of managing memory and properly allocating registers is all offloaded onto the compiler to convert down to imperative machine code. Rather than targeting machine code for each architecture by hand, an alternative target is the LLVM. The LLVM project is a collection of tools and libraries for making compilers and other related tools. A key part of LLVM is this intermediate representation, or IR. It's a typed low-level language intended for compiler front ends to use as the target. And the great thing about targeting the LLVM IR is that these front ends can invoke LLVM tools to compile to a wide variety of platforms and architectures: ARM, x86, Linux, macOS, Windows, even the web via WebAssembly. Additionally, the LLVM optimizer is able to take IR generated from compilers and, as the name implies, optimize the IR and perform actions like constant folding, tail call optimization, dead code elimination, and so on. A key part of the LLVM IR is that it's written in a strict SSA form, static single assignment. This requires every variable to be defined exactly once. They can't be mutated. So now the question becomes, how do we convert these functional features like hyperfunctions, closures, pattern matching into this SSA form? And that was the motivation behind this project. As seen here, we have a heavily recursive function known as Acma function, written in the project's Scala-like language. We're able to compile it with the generated IR displayed here on the right. And note how these nested recursive calls in the final else branch have now been broken apart into two separate calls because of the SSA restriction we have. We can actually now manually invoke the LLVM optimizer on the IR we've generated here and see what's able to do for us. And as you can see, quite a bit has changed. There's mentions of tail recurse in the comments and labels here. There's not only one recursive call in the entire Acma function. The optimizer was able to remove the other redundant recursive calls in favor of the loop, and we didn't have to implement that in our compiler front end. There's a couple more examples of features being converted to the IR. There's the implementation of an enum type in this language for this project, along with this nested pattern matching statement. The IR on the right here shows that, firstly, these enums have been converted to numbers. So Monday gets 0, time gets 1. Secondly, these match statements are now a series of if-else statements that invoke the print function on each terminating branch. Here's an example of a user-defined type for a student that takes an age, whether it's a part-time student, and what the student's grade is. We have a small isFirst function that determines if the current student's grade is enough for a first, and the main function here prints the corresponding result out. Something unique for this case is the introduction of a new type within the generated LLVM IR itself, reflecting the student's struct in the source code. To create an instance of this type, we allocate memory to it in the main function, and then we use this getElementPointer instruction to calculate the memory offset needed to store each element. And the isFirst function does the same to load the necessary elements from the type we pass in. Here's a more interesting example of an implemented feature, and arguably the hardest to carry out. Here we've got a function foo that takes an integer and returns a function. Inside foo, we've defined a function bar that also takes an integer and adds both integers together. And then we return the bar function from foo. In the main function, we call foo and store the returned function in this add variable, and then we call add and print the result. If we turn to the LLVM IR on the right, the nested functions have been split into two distinct functions, and we also have this env type here at the top. What's going on? Well, the LLVM doesn't allow for defining functions inside other functions. So we need to somehow compile bar in a way where it's removed from the body of foo, but it can still reference both variables inside it. It's known as a closure. This is done via the following process. First, we traverse the entire program and analyze each function. We check if the function contains any free variables. There are variables referenced inside the function but aren't defined inside the function. Foo here only defines the bar function and returns the bar function, so there are no free variables here. Bar, however, does have a free variable here. X is not defined inside bar, but outside it in foo. If we want to remove bar from the body of foo, we need to somehow maintain a reference to X. This is done by defining an environment that contains a reference to all the free variables that we want to use, in this case an integer, and we also pass in a pointer to the function the variable is found in, so bar. Now we have this environment, we can rewrite the body of the function by substituting the free variables with a reference to this environment. We do this by passing in the environment as a parameter to bar, and in the body we index inside the environment to retrieve the value of X. Next, we shadow the reference of bar with a reference to the new environment instead of bar itself. We pass in X, which is the free variable we refer to inside bar. Now we run into an interesting problem here. Remember that the LLVM IR is a typed representation. Well, here we've actually modified the return value with a different type. We're not returning the function directly anymore, we're returning this environment, this closure. So we need to traverse the program again to locate all the references to foo here, including the function calls, and adjust the type definition to match our new environment. We now have one final change to make, which is when we call the closure as a function. This is the reason why we embed the pointer to the function inside the environment, as we can now change all call sites to use the function pointer, passing in the same environment so we have access to the free variables we need. Now bar's fully closed over with no reference to free variables, with the closure properly propagated through the program. We can now simply hoist the bar function outside of foo and then translate all the function units to the LLVM IR as is. Similar to structure types, the references to the environment use getElementPointer instructions to index and appropriately load or store the values needed. So we've implemented these features into a language and compiled them down to the IR. Now the question is, how does it perform? Is it actually a viable target? One way of measuring performance is to see how well recursion is handled in programs. Here we benchmark the Ackermann function, as we saw before, and the Fibonacci function against Haskell, compiled with GHC, C, compiled with Clang, and the compiler in the project. There are two interesting trends here. First, Haskell is considerably slower than the other two languages. This could be down to its unique lazy evaluation strategy, where it's suboptimal in certain situations like these. Having said that, in the final Ackermann test, only Haskell was able to actually execute the program without crashing for the non-optimized runs. Secondly, C and the project perform very similarly, even identically in the optimized cases. With no optimizations, there are subtle differences as seen in the graphs. However, the LLVM optimizer is able to perform the same optimization passes across both of the IR, resulting in the same levels of performance when optimized with -03. Quite impressive considering that no effort was made in the project to optimize these situations. Just by targeting the LLVM, we're able to make use of these optimizations for free and achieve the performance levels matching C. Of course, there are always going to be improvements that could be made to how a compiler is implemented, even with well-established compilers. For this project, there are some limitations that make it more difficult to expand the feature set of the language, and others that are nice to haves, where most functional languages have them implemented. An improvement of the type system, such as implementing the Hindley-Milner system, would go a long way into making the type system more robust, as well as improving the language syntax by removing the need for type hints. A nice to have would be the implementation of some types to use pattern matching, allowing for types to be associated with values. A small example of how that would be compiled is shown here, where each variant is given its own LLVM structure type, some tag to distinguish between them, along with the data type associated with it. Finally, the current implementation doesn't use the heap at all. Using the heap would either require providing explicit memory management functions like malloc and free, something that functional languages don't typically implement. The other alternative is implementing a garbage collector, which would require a big overhaul in how variables are allocated and passed between functions. And this concludes this presentation on compiling a functional language by targeting the LLVM. Thank you for watching.